Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video. In this episode, we're going to be looking at parallelograms and the Pythagorean Theorem. The thing we're interested in with parallelograms is actually their area. So we're going to remind ourselves how to calculate the area of a parallelogram. And we'll start with a parallelogram where all the angles are 90 degrees. In other words, it's a rectangle. Now we know that for a rectangle, its area is its length times its width, or base times height. Now why is this true? So for example, if I took something like a rectangle that was 4 units long and 3 units wide, we measure area in square units that are little squares that are the same length and width as our base unit. So if I do that, I end up breaking this thing up into a bunch of squares. 4 this way, 3 this way. So how many squares altogether? 4 times 3, or just 12 of them. So that's why our area equals length times width in a rectangle. Now, what happens if we sort of tilt that rectangle a little bit so that the angles are no longer 90 degrees? Well, now we would call one of the sides the base. Doesn't matter which one we use. And we would call the distance between that side and the side that it's parallel to the height. So that's going straight in at 90 degrees. Now, notice when I do that, I've got a little triangle in the corner there. Now imagine I cut that triangle off and moved it to the other side. Now I'd be left with a rectangle whose length is b, whose height is h, and so the area is going to be b times h. So that's where that comes from. Now, you might ask, well, what happens if we really move this thing over so that it doesn't have just a triangle at the end? Well, we can go through the same process. We can take that shape, cut it off, move it over, and it's still sticking out. So let's cut that part off at the end, move it over, and again, we've got a rectangle that's b by h. And no matter how extremely stretched out this thing is, we can always do that. It's just we might have to go through the process multiple times, but we're always going to end up with that rectangle that's got a base b and a height h. Now, a really interesting consequence of this is I can take a parallelogram, keep its base the same length, keep the height between the two sides the same, and if I move this thing around, I get all kinds of different parallelograms, but because I'm not changing the base or the height, the area is always the same. So this is going to be really important for what we're going to look at with the Pythagorean theorem, is that we're going to be able to take these parallelograms and transform them to new parallelograms, different looking shapes, but the area is going to be the same. So now let's re-examine our old friend, the Pythagorean theorem. So we'll start with a right angle triangle with sides A, B, and C. We're going to build squares on each of those sides. And now I'm going to extend the sides of the two smaller squares so that they join together and make a little rectangle down here. I'm going to throw in the diagonal of that. And now, because of the way that I've done this, this little triangle that I've done down here had sides A and B. It's right angled. So I look at it, this triangle down here and this triangle up here are exact copies of each other. So this guy and this guy are exactly the same thing. Now, if I extend that diagonal right through the triangle and right through the bigger square, look what happens. This angle over here is opposite to this guy, so it's exactly the same. And now if I look at this little triangle here, it shares two of the angles with this other triangle. And we know that angles in a triangle add up to 180 degrees, which means that that third angle has to be exactly the same as well. So this line through the diagonal that continues is perpendicular or 90 degrees to the hypotenuse, which means that since this thing is a square, this is actually going to be parallel to these sides of the square, and that becomes really important. Now, let's use our properties that we just discovered of parallelograms. Let's start with the square that's on side A. And we'll use that property that if I keep the base and the height the same, the area is going to stay the same. So I'm just going to shift it down like this, keeping that height the same. So this area is the same as the original square. Now I'm going to do it again, except this time I'm going to use this as the base and this as the height. So when I do that, I can shift it over there. And if I do it one more time using those same sides, I can shift it there. So what I've done, because in all of those cases I'm moving and keeping some bases fixed and the height between them fixed, it means that that chunk of the big square, that rectangular chunk, has exactly the same area as this square on side A. And you could probably see where we're going with this. If we do exactly the same thing for the smaller square, we take it, we scrunch it over one way, we scrunch it again, we scrunch it again. The area of that rectangle is exactly the same as this square down here, which means that the sum of those two areas together is the area of the big square, which again is our Pythagorean theorem. So we've used properties of parallelograms to actually prove the Pythagorean theorem. I hope you enjoyed this episode of Math Shorts. Stay tuned and come back soon, and we'll have another episode for you. Until next time, keep exploring.